Our goal today is to finish 5-2. There is a problem with question 5 on 7-7. Basically, the values x, not x1, x2, and x3 are not the right values. And they should have been the x coordinates like 0, 3, 8, 6, 8, 9, 8, but they don't do that. So don't worry about getting a whole load of crosses on question 5 from 7-7. It's the one to do with the p-naught and you're trying to find the area. As long as you get the area correct, then that's good. And I'll just go back and make sure everybody just gets the points for it, right? I can't change answers on WebAssign. I don't think they are, you know, it's like write only or read only, whatever you call it. I'm just not allowed to change them. So question 5 and 7-7, don't worry if you got a whole load of x's to do with the values for x0, 1, 2, 3. Just ignore that. Just make sure you get the area right and you're good to go. So let's get started on 5-2. I want to give you a formal definition. Essentially our goal today, and it will happen, is we'll get the questions that you need to know about in 5-2 finished. And then whatever time we've got left, we'll start going back and looking at antiderivatives. So imagine I want to find the area of this nice curve y equals f of x from x equals a to x equals b. We actually have, oh, that's an interesting comment up here, right, called the fundamental theorem of integration part 2. There's a part 1, which you'll find out about sometime next week. Part 2 is the important one. That's the one that we use. Part 1's not that important, so we don't use it much. What it says is, if you've got a smooth continuous function f of x, so this idea of using antiderivatives to get the exact value for the area under a curve only works for well-behaved functions. So you don't want weird vertical asymptotes. Can you imagine trying to get the area under a vertical asymptote? Well, probably wouldn't end well, right? So we just ignore those and say, look, as long as it's a nice curve, right? Nothing weird going on. It goes up, it goes down. We're all cool. Then for a smooth curve, f of x from x equals a to x equals b, the area under the curve from a to b of f of x, that's essentially what that is, it's equal to capital F of b take away capital F of a. In other words, the value of the antiderivative at b take away the value of the antiderivative at a. So all you really need is essentially to find the value of the antiderivative at 2 places. So here is my first example of that. Question 3. Not question 3, sorry. The wrong place. Question 9. There we go. And we're being asked to find the area under the curve of, in my case, 7x. And what we do here is we find the antiderivative of 7x. Now, can you remember yesterday the antiderivative is add 1 to the power and divide by the new power? Because essentially what an antiderivative is the function that you would need to start with, that if you differentiated it, you would get the answer 7x. Would you agree if you differentiated this, you would get 7x? And we call this an antiderivative, and the rule I'm using is called the power rule. Add 1 to the power and then divide by the new power. What we're then meant to do is evaluate this antiderivative at 2 and at 0. And the way that you'll see almost every textbook that I've ever seen is that we use this little notation. We just do a big long vertical line and we do x equals 0 to x equals 2. And that's indicating the values that we're going to use. And so that's going to be 7/2 times 2 squared, take away 7/2 times 0 squared, and that's 4, so I guess it's 28/2, take away nothing, and that ends up being a really nice answer. It's 14.
Why does like this work? Or is it like really complicated?
It is really complicated. It's essentially works because when you do Riemann sums and you take a Riemann sum and you do that limit as n tends to infinity thing, remember that horrible thing that we did yesterday that took about 20 minutes and we got the answer a quarter? If you use that method in a more general way, right, where A is the start value and B is the end value, and you do everything else as general as possible, what you discover is that for any straight line, which this is, the answer looks like that. And for a quadratic, it looks like this. And for a cubic, it looks like this. And then they can just generalize it to x to the n. So it's really quite messy and quite complex. But the good news is it works. And it's really,
Thank you.
It's really nice. I mean, if I asked you to do that same question, can you imagine you try to do it with the trapezoid rule with 20 strips? Do you really want to have to do it that way anymore? No, most people will say, thank God there's a shortcut. And here is our next one. The area under the curve from 0 to 7 of x squared dx. And in this case, the antiderivative of x squared is add 1 to the power and divide by the new power. Evaluate it at x equals 0 to x equals 7. In this case, it's 1/3 times 7 cubed. Take away 1/3 times 0 cubed. I'm not going to do 7 cubed in my head. And the answer you get is 343 thirds. And so what essentially takes a minute to do using the fundamental theorem of calculus, integration part 2, takes what? Less than a minute, as long as it's not a complicated function. Let me do one more, but just add a little bit more to it. So suppose I want the integral from 1 to 2 of 3x squared plus 4x take away 2. So that would basically be a big, can you imagine a big concave up quadratic? Right. Let's take the antiderivative of each one. So that's a nice rule. If you want to get the antiderivative of a function that's made up of 2 or 3 bits added and subtracted, you can simply just take the antiderivative of each piece. So add 1 to the power, divide by the new power is x cubed. Okay, what would 4x get me if I take its antiderivative?
2x squared.
Agreed. I always think numbers are a special case. You know, what's the antiderivative of the number -2?
(2x).
Well, with a negative, yeah, -2x. And then you evaluate it at x equals 1 to x equals 2, just in case you think that it always has to be 0 to something. It can be any number to any other number, right? Now, if you plug in 2, you get 2 cubed plus 2 lots of 2 squared, take away 2 lots of 2, subtract 1 cubed plus 2 lots of 1 squared, take away 2 lots of 1. That's 8. That's 8, take away 4. And that's 1, add 2, take away 2. So that's 12, and that's 1. And so the answer is 11. That's very, very elegant, isn't it? Very quick. Find the antiderivative, evaluate it at the 2 numbers, start and finish, and subtract them. Are we good? Right. Now, as I said, our job today is to finish off 5.2. And 5.2's got a lot of little bits and pieces, right? There's not a lot of theme to it. They're not all the same kind of question. There's a couple of questions, just like the ones I've done, and I've kind of covered those. Those are questions 9 and 10. So I'm now going to go and kind of talk through some of the questions and then show you how to do others. Because some of them are just repeats of things we've done in the past. In question 1, here is a table of values, and we're being asked to find the area between 10 and 30, right? So that's the guy we're going to get our numbers from. And we have to use 5 intervals, which is fine. And I've got a lower and an upper estimate. Now we have 5 techniques, right? Numerical techniques. Left 5, right 5, mid 5, trapezium 5, and Simpson's 5. Okay? 5 different techniques. And it's asking us for a lower estimate and an upper estimate. Which 2 should I use to do that question? From the list of 5 I gave you, which 2 would you use to get a lower and an upper?
Left and
Left,
right.
right?
Yeah, I would use left and right. Do you notice that this table is an increasing function, isn't it? And if you're an increasing function, doesn't that mean that one of the left and right is going to be an underestimate and the other one's going to be an overestimate? So although it didn't say find L5 and R5, do you now understand that that's kind of a coded version of what that is saying? Now, in this question here, it says midpoint, so M4. No arguments about that, right? Just normal number crunching. Another midpoint, and that is kind of what we've been doing for most of this week. So the first 4 questions are not really any different, are they? It's just boring number count. Now, this fella here, we touched on yesterday. Remember those Riemann sums where we put this thing together? This here is a Riemann sum for the exact value of some function. And what we're being asked here is to fill in what this limit is and what the expression that goes here. Now let's get the easy one. They've kind of told you. Do you see the 0, 8 means this is 8? That makes sense. Now, what goes here is what function are we calculating the area of using this Riemann sum? Now, the one we did yesterday was an uglier version. Remember, instead of delta x, we used b minus a over n, right? And all that kind of thing. But everything you need to know is here. This bit here with all the xi's in it. And let me write something down that one of the students in the other class noticed and I didn't. And it was thrown them until I said, oh, I see what you're getting at. In this question, you have an xi, and it looks like that. And it also has a sigma, and it has a limit as n tends to infinity, and it's got other things going on, right? And it's got a delta x here. We've already said that it's 0 to 8. This bit here is the function, and the function is actually x over 7 plus x. Now, what was thrown them was, that's what it looks like on the screen. It should actually be more like that. Do you see it's a little x subscript I? Now, when you see it that way, can you see that that's basically the x's? And do you see how easy that question now becomes? Because he was seeing like an x times I, because it looks like it, but it's not, it just looks like it, right? And that's what was throwing them. So if that was making you think a little bit, hopefully that's helped, that it's just WebAssign's not very good at subscripts, I guess. Does it look more like a subscript now that I've mentioned it and less like an x times I? Okay, so in this question here, if you click on that, you hit the fraction button. If you want to get e to the power of xi, where the heck is that hiding? Under functions, I believe. There we go, e to the power of x. And that's that bit, and on the bottom, 7 plus x. Okay. We're cool with that question now? Okay, here's the next one. What number goes, this is question 6. What number goes here?
8.
Okay, what expression goes here?
X square root 7 plus x cubed.
Okay, so there's an x, and there's a square root of a 7 plus. Hopefully you're getting more comfortable using this little math pad at the other side, right? And what, 8 goes there? Looking good? Can I just say, same idea, right? The last two are just like the ones we've covered. There's that question 9 or a version of it. There's question 10. We're almost finished. And then we can start looking at the next session. So where are we going? Here is a function. And we are being asked to find the area under the curve at different start and finishing points. Let's take as an example then. If I wanted to find the integral from 0 to 8, which is question A, right? Wouldn't I need to find this area here? It's a trapezium, do you see it? Okay, I would look at that as a rectangle on the bottom and a triangle stuck on its top, right? Now the rectangle is this 2 boxes at the bottom here, right? And that would be 8 units long by 4 units high. So that bit would be 32. And then I've got a triangle, and triangles are half the base times the height. And a half of 8 times 8 also happens to be 32. So the answer to that question would be 64. Are you comfortable about how we just use geometry to find areas under curves? So as long as it's straight lines, rectangles, or bits of circle, we can do that. Let's suppose I did the integral from, what's that, 20 to 28. So that's this bit here. You see this little piece here? Now it's a triangle. And so it's 8 by 24, right? Each box is worth, is it 8? Oh, 8 by 12, sorry, right? 4, 8 by 4, 8, 12. And half of 8 times 12 is 4 times 12. The answer to that isn't 48. It's almost 48, but it's 48 with something extra tagged on with it.
Negative.
It's negative.
Negative
So,
48.
right, so when a curve is below the x-axis, the integral, the area that represents it, is a negative amount. And we talked a little bit about it's okay to have negative numbers in these questions. Totally okay. And then they've got a really weird one at the end. Can you see anything weird about question F? It's the only one like it. What's weird?
Going from 8 to 0, it's going backwards.
Going backwards. Now, we know going from 0 to 8 was 32. What do you think 8 to 0 would get you?
Negative that?
Referring to the same area, correct?
No, not quite. 32 is the same. But someone mentioned negative 32 rather hesitantly, and it is negative 32. Now, that doesn't necessarily transfer into a picture that you can see. It's more to do that if you switch the order of something, you're going to switch the answer from a plus to a minus or back, you know, vice versa, right? It's going to change the sign. And that's just really what that is. So here we got a guy here. If I asked you for the integral from here to here, which is this bottom piece, right? Where does that start? 5, 10, 10 to 30, right? So what one would that be? Oh, it'd be this one here, right? From 10 to 30. Would you agree that's just half a circle? Okay. What's the radius of this circle? If it was a complete circle, what would its radius be?
2.
2 boxes, but how much in units does that represent? 10, right? Each box is worth 5, so it would be a radius of 10 units. See, it goes 5, 10, 15, 20, 25, 30. So from here to here, right, those 2 boxes represent a distance of 10. Right, now the area of a whole circle is pi radius squared, so that would be pi times 10 squared, that's 100 pi. But we only want half of that because it's half a circle, and I'm going to do a deliberate mistake. Half a circle is 50 pi, and there's 50, and you have to hit the little Greek letter, and you have to put pi in. What's wrong about my answer?
It's not negative.
That's it. Do you notice that we want the exact value in these questions? And sometimes that means you're going to write the answer, especially later on next week, you're going to write the answer in some really ugly ways. I'm not going to turn it into 3.1412 and write down what the decimal is, because that's not an exact answer. Isn't pi one of those decimals that goes on forever, right? So we expect you to write it as 50 pi, 2 pi, minus 20 pi, things like that. You're also going to have in some questions, can you imagine that the area might be the square root of 7? Or e cubed, right? Or 3 over pi, or almost anything, right? Are we cool with that idea that you could have exact values that don't necessarily look like a number like 42, right? An exact value is 5 pi, or 5 square root of 7 plus 1. They count. Don't, what would the rule be? Don't go near your calculator, right? For these kind of questions, don't try and take the answer and just take it one step further and make it a decimal. Nothing good comes out of that.
As a rule of thumb, are we only breaking it down like to the decimals? Like if the question specifies like, you know, round to 3 decimal places, round to 2 decimal places, is that kind of a good indicator to bust out the calculator?
Yeah.
Okay.
That's a good way of looking at it. So you're typically only going to do that decimal stuff and the rounding off when it's a Simpsons trapezoid or round me off to 2 decimal place kind of story, right? In these later questions, which are probably going to be the vast majority that you're now going to see, it's going to be exact values all the time. So exact values, you leave it alone once you get to 2 pi. You stop. Don't go near your calculator after that. Well, time to start the next phase. We have covered enough for us to do all your homework for this week. So let's get a start on next week's homework. And there is nothing wrong in you getting a head start. Make sure you do the homework that is due by this Sunday, but get a head start on the other stuff. So let's focus on finding antiderivatives. Let's see what that looks like. Now, the guy I'm going to focus on today is only going to be one situation. Multiples of powers of x. And this particular one is very useful. It gets used an awful lot. I tend to describe this formula in English. I normally say add 1 to the power. And then divide by the new power. For my brain, this rule, which by the way, is also called the power rule, is very helpful for finding antiderivatives. Right. So for instance, if I wanted to find the antiderivative of 7x cubed, you would add 1 to the power, and then you divide by the new power. Be comfortable with that rule? If you say it in English, it's easier to understand. If you give me 4x to the 10, I will add 1 to the power, and I will divide by the new power. Now, technically speaking, all these antiderivatives should have what's called an arbitrary constant added onto them. Why, if I'm a bit like a lawyer, why do I need to put that in if I'm talking about an antiderivative of someone? Why do you need a plus c?
Because that would be canceled out in the opposite direction, so you never
Yeah.
know.
You
It's
never know what it's.
impossible. It's
Yeah.
impossible to know if it's there or not.
So we cover our butts, right, by saying plus C. It's a number, it might be there, it might not, it might be 42, it might be a million, but whatever it is, plus C covers it, right? And we're good. Seem reasonable? Now, let's write it down in another way. If you write the integral symbol, that's what that is, but you don't put limits on it, it's called an indefinite integral. Right? If you don't tell me what number to start and finish with, it's an indefinite integral. When I see a question like that, what I think to myself is, oh, you just want me to write what the antiderivative is, and you're correct, that's what they want. So the answer would be, just as you'd expect, what's that guy? Let's try another one. What would the antiderivative or the indefinite integral of that be? Anybody?
1/2 x to the 4.
Yeah. Did you notice that you quite rightly added one to the, added one? Darn it. Added one to the power and then divided by the new power, but shouldn't 2/4 always be turned into a half? Right? I call things like that style points. You should always make things as nice as possible. That is an indefinite integral. So what does a definite integral look like? Well, that's an example of a definite integral. So indefinite. Do you see the only difference between the two is that in the second case, you actually give a start and finish value. So in the context of what we're doing, won't that represent the area under this curve, starting at 1 and finishing at x equals 2? So if you're doing this question, won't your answer be a number when you're finished, right? It'll be an area under a curve. It's still going to use this guy, evaluated at x equals 1 and x equals 2. And then you plug in x is 2, and then you plug in x is 1, and you get 2, 4, 8, 16. A half of 16 is 8, and you get 8, take away a half. And I'm now going to do the wrong answer. 7.5. And hopefully you're saying, but it is 7.5. Because in one sense it is. But for style points, it's the wrong answer.
We still need a plus C.
No, we don't need a plus C. And I'll come to what Sabrina is talking about in a moment here. Because where's the plus C's that you were talking about? You know, you've kind of forgot about them now, and you told me at the start you should have them, and now you're telling me you're not. I'll explain why I don't need that. Are you happy about that guy is the same value as that? So what are the rules? There are lots of little baby rules in style points, but typically one of them is that for some reason or another, mathematicians do not like mixed fractions. Make them what you call improper fractions. I like the Scottish name. It's top-heavy fractions. I think that's a much better name, but whatever, right? We want these fractions. Now, to do with the plus C thing, let me show you why that answer doesn't have a plus C in it. So I'm going to go and pretend I'm doing the question from scratch. Only this time, when I write down the antiderivative, I'm going to put that plus C in. And so I'm going to get 1/2. Where did that 4 come from? 2, there we go. 1/2, 2 to the power of 4, add C, take away 1/2, 1 to the power of 4 odd C. This is 8 odd C. Take away 1/2 odd C. That becomes 8 odd C. Take away 1/2 odd C. And do you see that the C's cancel out and eventually you get 15/2? When you are finding a definite integral, right, ones with a start number and a finish number, do you see why we don't bother writing all those plus C's in? Because won't they always kill each other off in these questions? And since we know that that's every single time going to harm, can you see that mathematicians, being a bit lazy, say, ah, to heck with it, we'll just not bother writing it because we know it doesn't matter. I guess realistically, it is there, we just don't bother writing it. How about that? Right? The plus C's are there, we just don't bother writing them. How about that? You're cool with that? How about mixing things up? Let's just go back to finding antiderivatives again. I want to find the antiderivative of a square root. Maybe the next time it's going to be a cube root, whatever. Help me out here. I want to be able to use the power rule. Is there a better way to write this fella so that I can use the power rule on it?
Wouldn't it just be 8 times x to the 1/2?
It would exactly be that. Now, you might think, but isn't that power rule only for x cubes and x squareds? No. Nowhere in that description did I say n has to be a nice number. Agreed? N can be any number. Well, with one very minor exception. It can be any number you like. So now I can do its antiderivative, which is add 1 to the power. Now, then you should be dividing by 3/2. And to reduce the amount of lines of working I need, see if you tell me to divide by 3/2, isn't that the same thing as multiplying by 2/3? Would you agree dividing by 3/2 is the same as multiplying by 2/3? So are you happy where 8 times 2/3 gets me 16/3? Are you happy about where that guy comes from? Right? Add 1 to the power and then divide by 3/2 is the same as multiplying by 2/3. But that is not the style point answer. Style points, making it look pretty. Obviously, there's things like, 2/2 should be a quarter, right? That most people wouldn't even think of that as a rule. They do it naturally. But one of the major rules is the answer should look like the original question. Wasn't the original question 8 square root of x's? Shouldn't the antiderivative look like that guy? Which means that we really should, that is the style point version of that answer. Does that make sense to you that we're sticking to a consistent rule? Why do we stick to these? There's lots of reasons, but one of the major reasons is that if people in China and France and Germany and Venezuela, wherever, are doing calculus, when they do this question, their answer will look just like mine. Doesn't it make life easy if we all finish at the same destination? Can you imagine as questions get uglier and uglier? There could be lots of different ways of writing them. And then I would have to look at the way he wrote his answer or she wrote the answer. And then I'd have to look at mine. And when I have to do one of those calculations, is that really the same answer as me? That's a lot of pain in the butt, right? Why don't we all just write the same answer and call it good? And so style points allow consistency in answers. It allows everyone to do it. So the rules are make it look like the original. That's rule number 1. Rule number 2 is factor the heck out of it if you can. But normally we don't push that one too much. So some people leave it alone and I'm okay with that, right? But make it look like the original Everybody agrees on that one. Factor the heck out of it, you know, try and collect terms, make them look a little prettier, thing like that. But that one's tends to be a little bit lax. And I'm not even sure the third one is a rule, but 2/4 should be called a half, right? And 3 1/2 should be called 7/2, right? That's nitpicky, but yeah, we use that rule a lot. Are we comfortable with that one? Now, let's do an example of a cube root. And I'll do it from 1 to 2 because I don't want to make my life too hard. And I'll put I'll put a 6 there, right? So if I want to find the area under this curve, a cube root would become that guy. Are we comfortable with that? Add 1 to the power. Now divide by the new power would be times 3/4. And if you do 3/4, darn it in space, that's a hard one. I wish I hadn't picked that. You get 18/4, which is 9/2. Are you happy with it being 9/2? If I screwed up, tell me now. Okay. Now, for style points, shouldn't that be the cube root of x to the 4? Right, make it look like the original. Here's an added advantage of making it look like the usual. Won't the final answer, the numerical answer, look a bit prettier if it's in terms of cube roots rather than something to the power of 4/3? Would you agree it would just look uglier? So you're going to have 9/2, the cube root of 2 to the power of 4. Take away 9/2, the cube root of 1 to the power of 4. 2, 4, 8, 16. So that's 9/2, the cube root of 16. And that's 1. So cube root of 1 is just 1. Take away 9/2. So far, so good. Now I'm going to be Mr. Nasty here. That's not the best version of that answer. It's 99% good, but I can do just a little bit better. And the problem with that is that you probably haven't done this since Math 99. Can you remember that you can sometimes simplify square roots, which you've probably done a lot of? Remember, simplifying square root of 20 ends up being 2√5, right? Do you know you can simplify the cube root of 16? And if you get this, you deserve some brownie points. Can anybody tell me how to set up the method that I'm going to use? I don't even need to know the answer, but the method I'm going to use to simplify that guy.
Wouldn't you turn 16 into 8 times 2? Because then the cubed root of 8 is 2. So it'd be 9 cubed root of 2? If my brain can function that far.
Well, you darn well got almost all of it done correctly. 8 times 2 is 16. The cube root of 8 is 2. And it would be that guy. So what you've got here is 9/2, the cube root of 2. Oh, wait a minute, you may have actually done the whole answer for me. And I didn't realize that because these 2's cancel. And I think you did say 9 cube root of 2, take away 9/2. So in which case you did it 100% right. And don't worry too much. But if I do something like that in the test, if the question's worth, 15 points or something like that, I'll give you 14 if you stop there. So it's not like it's the end of the world. And if you can see that, I'll give you another point to the end. And here's the bad news. WebAssign is not your friend. It is not your friend. If you write down the answer as x to the power of 4/3 plus c, WebAssign is going to say you're right. And it's not right. You haven't written down the answer in its best form. So you got to remember that WebAssign's not a person looking at your answer. WebAssign's a piece of software. And in that software, it's designed to solve the problem, but it isn't designed to solve the problem with style points in mind. So it will accept the version that looks like that. It'll say, yep, you're right, but it will also accept the version that looks like this. So we just learn from that. Just because it says it's right doesn't mean that you've done it right, okay? So always have in the back of your mind when you're doing antiderivatives that you need to be aware of the style points. Let's do another. Another antiderivative. I want to find the antiderivative of that guy. And I still want to use the power rule. I'll take a suggestion. Is there another way I can write that that allows me to apply the power rule?
You can make it 1/4 x to the third.
Oh, wow. Think about that again. I think I know what you're saying, but it's not what I heard.
1/4 times x to the third.
No.
No.
No. It's,
X to the -3, 4 times
Yeah.
x to the negative.
that's what yeah. Do you see it now? Isn't the rule that I know it's, God, where did that appear? I don't know, it's hard to remember where things are. Is that 94 or Math 99? Where did you see that if you did it in this class, this college? I think it's 94. Does that appear in 94? 18 months ago? A long time ago for some of you? But isn't there a rule that that can be called a negative power? Okay, now I can do the antiderivative then. Add 1 to the power. Danger, Will Robinson. What number do you get when you add 1 to that guy? Oh, now you're panicking. It's okay to be wrong. I'm wrong 10 times a day, so go for it.
-2.
Yes. What is it not? It's not -4. How many of you, including me, how many of you, when you're just being careless and quick, have done that, right? Yeah, I've done it as well. Now, add 1 to the power and divide by the new power and then do a plus C. Style points, is that good or should we do better?
Turn it back into a fraction.
That's it. Because it should look like the original. Remember that rule? Okay, last question for today. You've not seen anything like this. I'm giving you 90 seconds. Find the antiderivative of that guy. Figure out a way to make it happen. Oh, Matthew, you think you got it?
Yeah.
Cool. Hold that thought. I'll be asking you in a few minutes. Well, not a few seconds, really. Is one of your answers 5/3 x cubed? And you've probably done it right. Okay, now Matthew's going to talk us through this one, but before I ask him, when you look at this question, do you realize that the power rule is just not going to happen in the form that it's in? For the power rule to happen, don't you need to have single individual powers of x? So that would have been my motivation to make it happen. So if you could tell us, what did you do first then, Matthew?
Essentially just distribute the dividing by x squared.
Right, there are two distinct ways you could say that. Both are equally correct. One of them is that you just broke this up, you distributed it like that. And the other way to look at it, and it does exactly the same thing, is to take the top term, the numerator, and multiply it, distribute it by the -2. Was it what this or that? Which one of those two ways of looking at the same thing did you do?
Well, I just kind of mentally canceled it
Right.
out.
So when you mentally cancelled it, it was a bit like this, but you just did it in your head.
Yeah.
Okay, so let's look at that one, what that gets you. These two cancel and they leave you a 5x squared. These two cancel and they leave you a +2. And won't this guy, because he's a kind of special case, won't we have to turn him into x to the -2? Right, 1/x squared needs to be called x to the -2. Okay, Matthew, what did you do next?
Then you can take the antiderivative at that point.
Okay, so this one would be add 1 to the power then, if I pick you up, and you got that one. Great. What would the number 2 get you?
2x.
And this one, be careful. What do you get?
That would just be -x. Or
Not
x to the
perfect.
-1.
Yeah.
Sorry. I just turned it into a fraction first thing, so I forgot to talk about that.
Right, are we cool? Oh, and of course,
Oh, and plus
let's
c.
see. Yeah. You see how that's a one-off question, right? But sometimes the thing they give you isn't what you need, right? You get this, but that's not what you need. What you need is this guy, right? And so you may have to work on it algebraically, right? And that can cause issues. So I want to show you a little problem. Well, it's actually two problems. You're that used to using the power rule that you see a guy like that and you say, no problem. I'll just write it like that and I'll use the power rule on it. Now let's see what the power rule would look like. If I added 1 to the power, I get x to the 0. Well, I can live with x to the 0. Uh-oh. But dividing by the new power, that doesn't end well, does it? So what on earth has gone wrong here? Well, what's gone wrong here is that technically the power rule is great for every single value you can have, except one. Right, sorry, except -1. Right, like this one. What is the antiderivative of this very special case?
Natural log of x.
Right, so 10 of them gets you that. So x to the 3rd power rule works. X to the -10, x to the 23rd power, all work. But you don't want to do it when it's just an x. Because when you have that, and all bets off and the antiderivative is something totally different from all the other situations. And if I convince you why the power rule doesn't work, right, that answer is just, well, doesn't exist, does it?
Is
Power
there
rule.
another particular like name for that rule? Like the other one's called the power rule. Does it change names at that point?
This one here?
Yeah,
I
'cause-
don't know if it would have a name, but if you want me to give you a name, I would say it was a log. I would just make up a name. I'd say 1 over x, the log rule. 1 over x gets you log x. I don't think it has a special name. I'm just making that up because I'm silly. Right. Now, I said there's 2 situations. So here is the second one. Here are 2 functions that are very similar looking. You agree? They're very similar looking. They're not the same. It's obvious that they're not the same. Oops. The rule is that if you use g, because some functions are called h of x and f of x and whatever. If you use g, its antiderivative is typically the capital of the same letter. So capital G of x is the antiderivative. What's the antiderivative of e to the x? We did that yesterday.
E to the x.
Okay. Now be very careful. That guy is not x to the power of e. That is not his antiderivative. What is the antiderivative of x to the power of e?
To the e plus 1 over e plus 1.
Yeah. Add 1 to the power and divide by the new power. Isn't e just a number? It just happens to be a number that's got its own letter of the alphabet. Isn't it 2.7128 and more? And you see how a function or 2 functions that look similar can have quite different antiderivatives. Oh, I just thought of one more. Definitely the last situation. Antiderivative of the number 2 is 2x. What is the antiderivative of e squared?
E squared times x?
Yes. Do you know what the mistake that some people will do? They will just think that the antiderivative of e squared is e squared. Antiderivative of e to the x is e to the x. Antiderivative of e squared, it's e squared. But it's not. Isn't e squared just a number like 2 is? And isn't the antiderivative of every number, whatever that number is, x plus c? So we get little nuances, right? Little sneaky ones that are going to, catch you occasionally, right? These kind of combinations, right? So you have to be on your best game that you don't fall for some of the little sneaky tricks that they play on you occasionally. And I'm calling that good. Say hi and bye-bye.